Good day, everyone. Today we want to consider ellipse, another challenging study in your coordinate geometry. But today we'll be simplifying everything about ellipse. I would like you to share your comments on the comment section about how easy this video has made you comprehend ellipse. And don't forget to subscribe, share, and like. And so let's go on to ellipse. You see, an ellipse is the locus of points such that the sum of its distance from two fixed points is constant. Let's explain that now. I have, let's say, a point here known as my focuses, or foci, sorry, F1, F2, and then I have a known point such that from here to that point and from here to that point, if I sum it up, let me say it gives me 10. I take on that point again. So if I sum here up with here up, I get 10 again. So I keep looking for points consistently such that the distance from F2 added to distance to F1 gives us a constant value. That's actually what came about the ellipse. So ellipse simply looks like this. Every point along this curve has equal distance from the F2 to F1. If you sum distance from here to here and distance from here to here, you will have same value along any other point. So that's what ellipse is all about. Next, we want to consider the properties of an ellipse. First and foremost, these are the two types of ellipse we have. Now, one thing I want to take note of is this. This point here is called the center of the ellipse. And this is our major axis. From here to here, this coordinate of this point here is known as your V2, and this point here is known as your V1. And so distance from here to V1 to V2 is what we call your major axis. And mind you, the distance from here to here is A, minus A. And distance from here to here is A. Now the coordinate of your vertex is given as your V1. Let me write that here. It's given as X1 plus A, Y1. And that's because this center here, the C, center C, has a coordinate of X1, Y1. Meaning the center is not at the origin. And so this is X1, Y1. Now, another thing we need to take note of here is our V2. Our V2 here, the coordinate is given as, since here is X1, this time from here to here is A. That will be X1 minus A, because you're going back, Y1. And this is the coordinate of your V2. We have another point here known as V3 and V4. Now, distance from V3 to V4 is known as our minor axis. And distance from here to here is called B. And so we can say this is given as X1, Y1 plus B. And for our V4, the coordinate is given as X1, Y1 minus B. And that's simply because distance from here to here is B, but you're going downward, so you say minus B. Now, the next thing we have is our focuses. Our foci. Focus is for one, foci is plural. This is my F1, and this is my F2. Our F1 has a coordinate of X1 minus C, Y1. Meaning my focus, the F1, is X1 minus C, Y1. This reason is because distance from the center to the focus is C. So please, this is plus, not minus, plus, because you're going forward. So x1 plus c, comma y1. Why our f2, the second focus, f2, is giving us x1 minus c, comma y1. And that's simply because distance from here to here is c, but we are going backward, so we subtract. This is my f2. And so that's about the focus and the vertices. Distance from here to here is our major axis, like I said. And distance from here to here, V3 to V4, is our minor axis. From the center here, C, to V2, or from the center to V1, is semi-major axis. And that's what we have here too, C, V1 or V2. And it's just equal to A. Why V1 to V2 is equal to 2A, since from here to here is A, and from here to here is A. That's 2A from V1 to V2. Mind you again that distance from here to here is B, and that make up our semi-minor axis, or from here to here, that's still B, semi-minor axis. So from V3 to V4 is our minor axis, which is 2B. Now, another thing we need to take note about the ellipse is the directrix. Our directrix is parallel to the semi-minor axis, parallel to it. This is our directrix. You can call this L2, you can call this L1, this line that goes like this. And so this our L2 is giving us x1 minus a over e. While our L1 is given us, I'm managing our space actually, it's giving us x1 plus a over e. And so that's that about our directrix, L1 and L2. That's the symbol. L is used to represent the directrix. Now, another thing to take note about the ellipse is the latus rectum, the distance from here that passes along the focus to this other side. Actually, we use Q2 and Q2 prime here, or here as well. Q1 and Q1 prime. The latus rectum is simply given as 2b squared over a. Next is the eccentricity. I didn't mention that. Eccentricity is just simply c over a. And the c is simply a squared plus b squared all into square root. Okay. Next thing we need to know actually is another type of ellipse that looks like this. The origin is here. Now this type of ellipse, again, from here to here will be our major axis this time around. So the major axis is along the y axis, or it's parallel to the y axis. And we can say that this is our V1 and this is our V2. I'm going to stay here to do this properly. So this is my V1, this is my V2, and then this is the center. The center always is x1, comma y1, and then we have our F1 too, F1 here, and F2 here. Now, mind you, in this case, the distance from here to this vertex is the same as the distance from here to this vertex, and that's still your A, just like we have it here. Our x1, V1 here is simply x1, comma y1 plus A, because this distance is the vertical distance, so it's added to your y. That's why it is y1 plus A. Why for this V2 now, the coordinate will simply be given as the V2. Let me write that here. V2 is simply x1, comma y1 minus A. And that's because we are going downward. We also have our V3 as usual, my V3 and my V4. In this case, our V3 is giving us x1, comma y1, x1, sorry, plus b, comma y1. While our V4 is giving us x1 minus b, comma y1. And that's because distance from here to here is b, and distance from here to here is also b. And so that's that for this ellipse. Now, we have also the focus. Our F1 as usual is giving us x1, y1 plus c. Take note. And our F2, which is the focus here, is giving us x1, y1 minus c. And so if you know all of this, actually, you can write the equation of your, or get the equation of your ellipse, or get whatever you're asked to know about your ellipse. I'm managing this space so that we can solve question and relate to it. Now, next is your directrix. Your directrix is parallel to your semi-major axis, always. And that's from here to here, or from here to here. We have the L1 and the L2. In this case, our L2 is giving us y1 plus minus a over e. That's your L2. While our L1 is simply giving us y1 plus a over e. So that's that about our ellipse. The lattice settlement is the same, did not change. And remember, in this case now, your major axis is parallel to the y-axis. Now, last thing to note is the equation of a parabola, of an ellipse, not parabola, sorry. It's giving us x1 minus x minus x1 over a squared plus y minus y1 over b squared. This manner equal to 1 for this ellipse. Now, one thing you must take note here is the very fact that if the center of this parabola, of this ellipse, I don't know why I keep saying parabola, of this ellipse is at the center, at the origin, it means that your x1 and y1 will be 0. And this will become x squared over a squared, because x1 is 0. And your y1 is also 0. That will become y over b squared is equal to 1. This is what it will become if the center is at the origin. For this ellipse, the equation is giving us x1, x minus x1 all squared over b squared plus y minus y1 squared over a squared is equal to 1. And again, if the center is at the origin, this will become 0 and this will become 0. And that will become x squared over b squared plus y squared over a squared is equal to 1. Now, the question is, if I'm given an ellipse, how do I know that it's of this form or it's of this second form? Just from the equation. Well, it's important to know for ellipse always that A is greater than B. And so, if you look at your denominator of your equation, if the greater value A is under X, it's of this very first form. If the greater value, which is still your A, is under Y, it's of this second form. Let's take an example now. Example 1. Find the 4 vertices, foci, center, and the length of lattice circle of x squared plus s squared over 9 plus y squared over 25 equals 1. Well, this is the equation of an ellipse. And obviously, it's clear that it's either of this type or of this type, where the center is at the origin. Since it's not giving us x minus something or x plus something. Now, the next I want to talk about is, if you look at here, the greater value is under the y. That tells me it's of this type, where the center is at the origin. Since the greater value is under the y, I can turn this to say this x squared over 3 squared plus y squared over 5 squared. Since 25 is 5 squared. And this is what we have here. If we compare with this, that will be x squared over, I'm solving here, solution, please. X squared over b squared plus y squared over a squared is equal to 1. So here we can say that our b squared is equal to 3 squared. Hence, b is 3. And we can say a squared is equal to 5 squared. Hence, A is 5. And then we can get our C. Remember, C is giving us A squared plus B squared all into square root. And that will be square root of 3 squared plus 5 squared. And that's square root of 41. We've gotten our C. Now let's get what we have to get in this question. I'm managing my space. Now first we are asked to get the vertices, our V1. Now, if the center is the origin, since we can say the center is at the origin, it means that, again, my x1, let me state that first, x1 is 0 and y1 is 0. So let's go with our vertices now, V1. Remember, this is your V1, that will be x1, comma, y1 plus A. So our V1 will simply be 0, comma, 0 plus our A in this case now is, what we have is 5. That's simply V1 is 0, comma 5. Again, for our V2, that's giving us x1, comma y1 minus A. And then we say that V2 will simply be 0, comma minus 5. That's our vertices, V1, V2. Now, let's get our V3, the other vertices, V3. That's giving us x1 plus b, comma y1. And that will be V3 is, our x1 is 0, we know that. So simply b, comma 0. Because y1 is also 0. Our b in this case is 3, that's 3, comma 0. And obviously our V4 is x1 minus b, comma y1. And the V4 will simply be given as minus 3, comma 0. So we are done with all our vertices. Next is the center. Obviously, number 2. The center, C, is 0, comma 0. We are done with this. Now, the next thing we are looking for here is the center, the foci. I ought to have done the foci before the center, but let me erase this now. The foci. Our F1 in this case is giving us x1, comma y1 plus C. And the F2 is giving us x1, comma y1 minus C. And so this is F1 into the x1 is 0, comma y1 is also 0, plus our C. We got it to be root 41. So my foci is just simply 0, comma root 41. And our F2 will be x1, comma, which is 0, comma 0 minus root 41. And our F2 will simply be 0, comma minus root 41. Then lastly is the latus rectum. Our latus rectum is simply 2b squared over A. And that will be 2 into 3 squared over A, which is 5. And that will give us 3 squared is 9 times 2, 18. That's 18 over 5. That's our latus rectum. So that's that for this question. Example 2, identify the conic section 4x squared plus 9y squared equal to 36. Find, hence find its semi-major axis and major axis, semi-minor axis and minor axis, eccentricity, vertices, equation of directives, and lattice, length of lattice rectum. To go with this, first of all, we can identify what type of conic section is it. Well, we have 4x squared plus 9y squared is equal to 36. Firstly, this cannot be a circle. Why? The equation of y squared and x squared are not the same. This cannot be a parabola, and that's simply because in a parabola, only one of the variables have squared, the other one is not squared. Now, this is either an ellipse or a parabola. So let's find out now. Dividing here by 36, and dividing here by 36, dividing here by 36. This will give us 4 here 1, 4 here 9. That is x squared over 9 plus 9 here 1, 9 here 4 will give us y squared over 4 is equal to 1. Where it is an ellipse, simply because there's no minus here. One of them we have minus actually. Well, now what type of ellipse is it? Well, since the higher denominator falls under the x, it's of this first type, but the origin is at 0. And so that's that. We can write this again as x squared over 3 squared plus y squared over 2 squared is equal to 1. And if we compare with this equation, x squared over a squared plus y squared over b squared, we would have as 1. Then we can say a squared is 3, and then a, that's 3 squared, and then a is 3. And we can say that b squared is 2 squared. Eliminating the powers, you can say b is equal to 2. And we can get our c to be equal to square root of 3 squared plus 2 squared. And that will go square root of 13. What now our c now? Now let's get our vertices. V1. Remember, our V1 in this case is x1, y1, x1 plus a, y1. That's my V1. But for this type of, since the center is at the origin, we can say that our x1 is 0 and y1 is 0. And so this is 0, 0. So since our V1 is equal to the a, our a is 3, 0. And our V2 is giving us x1 minus a, y1. And that will give us that V2 is simply equal to 0 minus 3, that's minus 3, 0. When our V1 and V2, let's get our V3. Our V3 is simply giving us x1, y1 plus b. And our b here is 2. So our V3 is simply 0, 2. Now let's go to our V4 and other questions we have to get here. I'll be raising this. So I choose to take question number 4 first. Now our V4, that's why I'm doing the vertices first. What's our V4? Our V4 is x1, y1 minus b. And that will simply be, let me divide this board into 2. So that will simply be our V4 being equal to 0, minus 2. Since y1 is 0, s1 is 0. I'm done with that. Let's get our semi-major ASICs, which is the first part of this question. Our semi-major ASICs is giving us A. And our A is simply 2. And our major ASIC, this is our semi-major. Now, our major ASIC is giving us 2A, which is 2 times 2. That's 4. This is giving our major ASICs. Again, number 2, we have our B, which is equal to, our A is 3, sorry. So this is 3. And this is 6. So that's a mistake. Our B is 2, which is our semi-minor ASICs. And we can say that our 2B, which is 2 times 2, which is 4, is our minor ASICs. And that's that about our major and minor ASICs. Next, we have here is our eccentricity. Eccentricity is simply equal to C over A. We've got our C already to be root 13. Root 13 over the A, that's 3. So we are done with that. Next is the equation of directories. We have our L1 and L2. Our L1 is simply equal to, you can say it's X being equal to X1 plus A over E. And so our X1 is obviously 0 plus, I'm erasing the other part of the question. Our A is 3 over eccentricity is root 13 over 3. So that will simply be that X is equal to, this 3 goes up here to multiply this, that's 9. 9 over root 13. That's our first directories. We have the second one, L2, and that's equal to X1 minus A over E. Obviously, if we do this accurately, following S1 to be 0 and A to be 3 and over E, we still have our X to be, this X is equal to, so this is going to be X is equal to minus 9 over root 13. If we do that accurately, this is our L2 actually, second directrix. And I think the last thing we are asked here is length of latus rectum. Our length of latus rectum is 2b squared over a. And that's 2 into b is 2 squared over a. And that is 3. This will give us 2 squared is 4 times 2, 8. 8 over 3. So that's all for this ellipse. Example 3. Write the equation of the ellipse 25x squared plus 4y squared minus 50x minus 16y minus 59 is equals 0 in the canonical form, and x determine the semi-major axis, semi-minor axis, coordinate of the center, coordinate of the foci, the vertices, eccentricity, equation of directrix, and length of latus rectum. Well, this is quite an easy one. The most important thing here is to get the canonical form. And so to begin with, we have 25x squared plus 4y squared minus 50x minus 16y minus 59 equals 0. From here, I will have to rub off the whole of this actually. Now, I can rearrange this to be 25x squared minus 50x plus 4y squared minus 16y is equal to 59. Now, factorizing this gives us x squared minus x minus 2x plus factorizing 4 here will give us y squared minus 4y. Now, I'm going to be making this a perfect square. You know, that will be add the square of half of coefficient of x to both sides. So, coefficient of x is minus 2. Half of it is half, like this, then square. That will simply be minus 1 squared. And that will be 25 into x squared minus 2x plus minus 1 squared. If I'm adding this, I'll add it to this side, and that will be, what we have here is 59. Pardon. Now 59 plus, but what do we add here? It's not just minus 1 square. Remember, this 25 is multiplying everything you have here. That will be 25 times, minus 1 square is 1. So 1 times 25 will give us 25. So what was added here is 25 and not minus 1. Take note. So I'm adding 25 to this. Plus again, I need more space. So now here, 4 into y squared minus 4y. I'm going to make this a perfect square. And what's the question of y here? It's minus 4. Half of it is like this, then squared. That will be minus 2 squared. And that will be adding minus 2 squared. But remember again, what was added here is not just minus 2 squared. Minus 2 squared is 4. But remember, this 4 is multiplying whatever is here. So 4 times the 4 you add will give us 16. So also add 16 to this other side of the equation, because the equal to separate this into two sides, here and here. Now let's factorize this. If we do that, remember how to factorize. In very fast way, pick out the terms that have square. Here we have x, we leave the square. We have minus 1 here, leave the square as well. Is it plus, this plus please, are not equal to. Plus here 4 into, pick the y and leave the square. This one does not have square, so leave this. This half square minus 2 squared is equal to, if you add up 59 plus 25 plus 16, you get 100. And so this is what we have now. Next is to make sure that here is 1. To do that, you divide here by 100. I'm not just going to divide here by 100. I'll divide everything by 100. Divide here by 100. Divide here by 100. Divide here by 100. And that will give us x minus 1 all squared over 25 here 1. 25 here is 4. That's 4, which we can say 2 squared. Plus 4 here 1. 4 here 25. And that will give us y minus 2 into square over 25, and that's 5 squared is equal to 1. What type of parabola is this? Since the higher value is under the y, it's of the second type of parabola. But mind you, the center is no longer at the origin, because we can see s minus something or y minus something. So this parabola is already in its canonical form, which is the first thing we are asked to do. Now, if I compare this with the general equation of the ellipse, not parabola, ellipse, pardon, of this type, the equation is x minus x1 all squared over b squared plus y minus y1 squared over a squared is equal to 1. So this is what we would have. In this case, we can now say x1 minus x1 is equal to minus 1. And so x1 dividing both sides by a minus will give us 1. And again, minus y1 is equal to minus 2. Dividing by minus will give us y1 will be 2. When our x1 and y1 to be 2, which happen to be the center of this ellipse. Next is to compare our b's and a's. Already, b square we know is equal to 2 square. So we can say b is 2. Again, a square is equal to 5 square. So we can say a is 5. To get our c now, we know that c is equal to a square plus b square all into square roots. And that will simply be 5 square because our a is 5 plus 2 square because our b is 2 all into square root. So c is equal to 25 plus 4. That's root 29. Having gotten this now, let's get other things we have to get in this ellipse. Let's begin with the very first one. 1. Semi-major axis. And that's simply equal to A. And our A is 5. That's good to go. Number 2. Semi-minor axis. And that's simply B. And our B is 2. We are done with that. Next is coordinate of the center. In this case, the center is simply x1, y1. So we can say our center is simply the x1 we got to be 1 and y1 is simply 2. We are done with that. Next is the vertices. We have our v1, which is x1, y1 plus a. That's our v1, and that will be v1 is our x1. We say it is 1, y1 we say it is 2 plus our a. Our a here is 5. So that will be v1 being 1, 7. Now our v2, which is x1, y1 minus a. That will be v2. Our x1 is 1, 2 minus 5 because y1 minus a. And that will give us our v2 being equal to 1, minus 3. That's good to go. Now, I skipped the foci. We'll come back to that though. V3 is x1 minus b plus b, y1. And that will be v3 being equal to our x1 is 1 minus b, that's 2, y1. This is which is 2. That will give us our v3 to be equal to minus 1, 2. And then our v4, which is x1, minus b, y1. That will be v4 being 1. This is plus, sorry. And that will be 3. And this 1 minus 2 this time, 2. Because y1 is 2. And that will give us v4 is minus 1, 2. Now let's get the coordinate of the foci. This is the 5th. I'm doing the 4th. If I skip the 4th mistakenly. Our f1 is simply x1, y1 plus c. And our f1 is going to be x1 is 1, y1 is 2 plus your c with 41, with 29. So this is the foci, f1. Let's get the f2. x1, y1 minus c. And that will be f2 being 1, 2 minus root 29. Now, we have to get our eccentricity. Our eccentricity is c over a, and our c is giving us root 29 over a, that is 5. And so, next, let's get our latus rectum. Latus rectum, or length of latus rectum is 2b squared over a. That's 2 times. Our b here is giving us 2 squared over a. Our a is 5. And that will give us 8 over 5. And our equation of directrix, the lastly. We have our L1, which in this case will be giving us x1, not x1, sorry, y1 plus a over e. In this case, our y1 is 2 plus our a is 5 over root 29. You can sum this up or simplify it. And then you can get our L2. Our L2 in this case will be y1 again, but minus a over e. So our L2, which is the directrix, is giving us 2 minus 5 over root 29. Sometimes it's giving us x is equal to this and x is equal to this. So take note of that. So that's that about this ellipse. And that's we want to consider under ellipse. Thank you and God bless you.